So yeah, before we start, just kind of give a brief introduction to Parsa. So he is a project engineer at Subsurface and Tunnel Engineering. Dr. Heydarpour is a performance-driven structural engineer with a wide-ranging background in both structural and geotech engineering. He has served in different capacities ranging from detailed analysis of existing bridges, building and utility lines in the vicinity of near-surface structures, construction sites, and also geomechanical modeling of stage excavations. So what I said is, Parsa can better introduce himself. And before we jump to Parsa's presentation, I just want to give a brief introduction to MIDAS Expert Network. So in this network, you can do or you can present webinars, you can listen or do Q&A session yourself. You can do one-to-one consultation, or sometimes when you're simply running into problems with the work and simply want to have your work getting peer reviewed, you're able to contact us and just to having us connect with an expert user to you and having that solved. We've actually done numerous cases and where engineers actually have their problem solved. And sometimes when you don't really want to go to tech support directly, and rather having some like one-to-one interaction, that's the right network for you. And how do you join? Simply go to this website, midasoft.com/MIDAS Expert Network. You can fill out the form and our team will contact you shortly. So without further ado, I would switch over the presentation to Parsa. And yeah. So
yeah. Okay, very good. Do you guys hear me?
Yeah, we can hear you.
Okay, perfect. So if you please give me the screen so I can share my screen with you. And right now, also, if you please activate Amir's headphones, headphones, so he can speak with us. That would be perfect.
Sure. Let me find Amir.
Parsa, we just sent him an unmute request. I think he should have received it.
Yeah, he's good now.
So that he can unmute himself. Yeah.
Okay, so while Amir gets on board, I just want to do a quick introduction to myself. My name is Dr. Parsa Heydarpour. I have received my master's from George Washington University, and I continued my work there, and I received my PhD in structural engineering in 2018. For about 4.5 years, I was working on a Caltrans funded project to analyze cylinder bridges. After my graduation, joined Subsurface and Tunnel Engineering, and we are extremely involved with underground construction activities, including tunnel design, including assessment of existing structures and lining design, and we provide a wide variety of services. And as soon as my colleague, Mr. Amir Medik Amir, are you there?
Yes. Hi. Good
Perfect. So if you please take over and give
Thank you. Thank you, Midas, for having us present, having Parsa
present.
Hi, Kyle. Good to see you. Thank you, everybody, for joining. Just real quick before I pass the baton off to Parsa and let him do his magic. Just wanted to introduce myself, and as you just heard from Parsa and our company, just briefly. So again, my name is Amir Medik, and I'm the senior project manager for STE. So I oversee a lot of the underground tunneling projects, and Parsa is a project engineer focusing a lot on the technical disciplines within our organization. So we are a multidisciplinary engineering firm, specializing in the management, planning, design, and construction of complex transportation, water, wastewater, and mining projects. So our staff, we have a few staff, and our staff have decades of experience in the disciplines of geomechanical, as you'll see with MIDAS, geotechnical, rock engineering, disciplines applied across various projects. We primarily are involved in soft ground and rock tunneling projects, NADEM projects, New Austrian tunneling methodologies, trenchless technologies, and in this presentation, as you'll see, we'll do shaft design and protection of existing structures, which is a huge component in many complex projects we've been part of. Primarily our philosophy is to produce adaptive engineering approaches through a combination of applied experiences. A lot of us have field experiences and modern engineering techniques, aka MIDAS. So with that, I'll pass it on to Parsa, and he'll cover over the shaft design, protection of structures presentation. And thank you all again.
Thank you, Amir. Okay. Do you hear me, guys?
Yes.
Okay, perfect. So now I'll take over and let's continue. So today, what we are planning to do is to go over a shaft excavation. And the first thing that comes to mind is, what is our objective? What do we try to accomplish here? In this slide, if you look, you can see that I'm putting a very regular townhouse located in Washington, D.C. And let's assume that you have a excavation very close to a building like the one that I'm showing here, and you want to evaluate what is the anticipated damage in that structure due to your excavation. This excavation can have any geometry, not really important whether it's a shaft, whether it's rectangular, whatever geometry it has, it's going to impact this structure, and you need to have approvals to make sure that you don't go beyond a certain damage level defined by your contract. In order to do that, in order to evaluate the damage induced in the structure, we need to actually know how the ground is settling. That's the magic to it. You need to know how the ground is settling in order to be able to see what strains are developed in the masonry. And that is where MIDAS GTS-NX comes to play. So basically what today we are trying to do is we are trying to look at displacements developed in the soil. So for someone who designed a shaft, is probably they are more interested to know what forces are developed in the structural elements. Today, as engineers, we are not the one who is in charge of optimizing the shaft design or the SOE design for the shaft. We are an engineer that is trying to realize if there is an excavation, if there is an excavation and there are a lot of adjacent structures, what type of impacts we are going to see in those structures. There are many different methods of looking at this. One of them is proposed by Mr. Berland, and in his research and in his work, he defines the strain as the major component to evaluate the structures. And basically, we treat the structure, the actual building, as a equivalent deep beam, and we look at the formations created in the structure. And these formations can be due to bending or due to shear, and all these damages can vary from all the way from just visual impacts, very small cracks that really nobody cares about, all the way to cracks that could jeopardize the stability of the structure. And obviously, as you have more displacements, the cracks will open, and you will have more challenges facing you. And here is in this slide, I'm trying to just give a presentation of different levels of damage that we can face, and it goes all the way from negligible, which is pretty much hairline cracks, 0.1 millimeter, all the way to cracks that are almost an inch in crack width, and they can jeopardize the stability of a structure and all other cracks anywhere in between. So as I told you, there are many different researches out there to try to quantify these damages. One of them is the one that's proposed by Mr. Berland and Ross, which we incorporated here at STE quite a lot to evaluate, especially Northeast Boundary Tunnel project located here in Washington, D.C. Using a software, you come up with the settlements that you have, and then you turn those settlements into displacements, and displacements into tensile stresses, and then you have a measuring tool that you can just evaluate what level of damage you should be expecting. So having this in mind, this is going to be the goal of this project, to have a structure. For example, you can see the footprint of this structure adjacent to the excavation. So basically, we can define investigation points, and these investigation points are going to be used to determine what settlements we are expecting. And based on those settlements, we can evaluate the building, see what type of sagging or hogging or compression or tension that's going to be exposed to the facade of the structure. And one other thing that I'd like to mention, that in most regular cases, in these projects, you consider greenfield assumption. In more sophisticated analyses, you might want to model the piles, model the bridge piers, you model everything, and then try to go above and beyond to get actual settlements. But in many cases, greenfield assumption is good enough, which means that we assume that there is absolutely nothing on the ground, and using the greenfield assumption, we get the settlements and displacements at the ground level, and we apply those to the foundation of the structure. For more sophisticated cases, here in STE, we have done many cases that we had to go way more sophisticated than a greenfield assumption, but for today's presentation, I believe this should suffice. So having this in mind, today I want to go over a few MIDAS tricks and MIDAS tricks in order to model a shaft, and let's see how far we can get, and if we have enough time, I would definitely like to go toward showing how to do dewatering, which is extremely important in order to get a realistic settlements. So I have few sample models here. Again, the mentality is the same, whether you have a rectangular excavation with a different pile, with multiple piles and different levels of strutting, or a simple shaft. The mindset is the same, only the application is a little bit different. And let's start. So I'm going to create a new model. And as you probably know way better than I do, in this page, you just go and set up what system you want to work with, and then hit OK, create a new model. And then I would like to go a little bit over how to define a geometry of the model. So I'm going to define a rectangle to work as the boundaries of my soil box. So I do 700, 700, and I will call this layer probably soil. And I like to do soil. So This is going to work as the boundaries of my soil box. And then I would also like to have a shaft, which is going to be a circle, and I do a radius of 15, and I like to call it excavation. So it's created here, and I need to move it. And one of the good things that I like about MIDAS is a lot of capabilities. It's been implemented in the program that gives you a lot of you'll be able to do a lot of things with MIDAS. That's one of the beauties about this program. Okay, so now I have my excavation. I have my soil box here. I have my circle that's going to act as my shaft. And now I also like to have a few cutting planes that I'm going to use to cut my soil planes and everything. So 0, 0, 1000, 1000. I would like to make a face, and I would like to call it cutting face. Cutting face. Apply. Now I have this. Now again, I'm going to use one of the very useful features that MIDAS has its own, has implemented inside. It's the copy feature. I want to copy this every 10 foot for 4 times. And this is a very useful thing to preview. Oh, okay, it just tells me I need to select the direction. Oh, forgot that. I do preview. It's wrong direction, I know. That's the beauty of preview. So you can see before applying. Cutting faces, apply. So now I have created all my cutting faces that I'm going to use later on. And I always like to put them in different, under different names. Later on, you'll realize how valuable this trick is to have them in different names. And now I'd like to extrude in order to get to my geometry. So select objects. I would like to do select edges. And then I would like to do a -250, definitely under soil. Apply. Then direction, we forgot to select direction. Apply. That is good, that's what I wanted. And then I'd like to do my geometry, similar. Select object, edge. I would like to do a 50 foot, a -50 foot. And then again, definitely under excavation, preview, apply. And now I have this. And as you know, when you have an excavation of 50 feet, you are not going to do it in one step. So you most probably need to divide it into multiple stages of excavation. That is why we generated these cutting planes. So what I'm trying to do now is I'm going to divide that one stage excavation into multiple, using these faces. We are going to tell the program that we want to apply this into multiple stages. So now if I turn my cutting planes off, now we can see that we have each later on when we define the different stages of excavation, each of these going to be excavated in at a different stage. So same thing can happen to your soil. So for example, you can have one layer of soil similar to what I have here, or you can have multiple layers of soil similar to what I have in this model. Generally speaking, the modeling is not really different, but if you have multiple layers of soil, MIDAS has the capability of applying that as well. So for this example, I would like to, for example, divide this into 2 segments. So later on, we should be able to assign 2 different soils. So we should be able to assign 2 different soil types here. Apply. Now, target object. 1 second. Because I need to hit escape. Okay, solid. Select target. There you go. Surface this one and this one. Fine. Okay. Now I can turn this off. Now I have 2 different layers of soil. So one other thing that we need to do is we need to make sure that our geometries are recognizing each other. So basically, when we have when we want to excavate, we need to make sure that as each stage the connections are properly done. And MIDAS has an auto connect feature here, so I can do this, and now we can see that basically now geometries are recognizing each other. So this is a very basic overview of things that we need to do in the geometry portion in order to model a shaft excavation. The most important thing in my mind is properly defining materials and properties. And MIDAS has quite a variety of different constitutive models that you can work with. And here in one of the files that I prepared for this specific session, I have defined all, so let me just, this is the file that I wanted to present. And the only thing I know how to do, okay, so that's fine. So let's just unlock this. So I just want to go over the difference. So for example, for the soil, I have done Mokulo, and you define all the properties that you need to do. Make sure that if you want to dewater, you need to define the unit weight of saturated. That's very important. If you have a structural member like steel rib, you need to make sure that you need to click on a structure so the porosity parameters no longer can be defined for a structure. And if you have a shell element later on, so that shell element can be your steel corrugated beam, your steel corrugated sheets, or you can have a concrete diaphragm if you want. You need to define them here, and later on you can define the properties, all the things that you have. Actually, I would like to go over, because in this model I also had the steel ribs, and that is also something that I would like to show you how we typically do it. So if you have this curve on, so let's say if you have 5 stages of every 10 foot and you want to have your steel ribs spaced at every 10 foot, again, you have this capability embedded in MIDAS that we can define, we can draw these circular sections, and later on we can assign them whatever geometry we want, and then they will, we mesh them and they will work as our steel ribs. So in order to do that, again, I need to use the translate option here. So I have selected my my geometry. I do every -10 foot for 4 times, and I need to do copy every 4 times. And I want to create a new one, and I call it steel ribs. I call them ribs. I add that here, and then I will be able to go and select ribs. I do preview, looks right to me. Later on, what we will do is we are going to select a proper W section, and then we will assign this geometry that a specific W section, and that should be good enough for us. And then we will mesh that, and that will act as our steel ribs. I hit OK, and now I have my ribs as well. So if I turn this off, and one good feature again MIDAS has is you easily can move things around. So if I want all 5 of them to be together, I can just drag and drop things. This is very handy feature that MIDAS has. I appreciate every engineer who is working hard to make this program just user-friendly. I'm someone who's coming from the background of FLAC, so I know what not being user-friendly mean. So let's go to, so now I guess we have properly covered the geometry. After this, the next stage would be meshing, which I have a model here. So I'll just give you a few. I show you how to do the meshing. I'm sure you know better than I do. I just always I recommend for 3D mesh. One good feature that MIDAS has is if you want to give some hint to the program that how you would like to mesh it, you can define nodes here, and later on, so for example, on each edge, I can define that I want, for example, 20 points, and later on the program will use these points in order to create the mesh set you have. So for example, if I want to select these points, these corners, and just tell MIDAS that I want to have, for example, 5 nodes on each one of these, later on I can use these nodes to guide the program how to mesh the geometry. These few things, these small tricks really become handy to have a model that is not too big and running time not becoming crazy long. Are you with me, guys? Okay. Are you? Okay, perfect.
Yeah,
so,
sorry, my internet just, yeah, sorry. Go ahead.
Oh, okay, sure. And then similarly, we can do, we can select edges for the circle, and we can just give divisions to this as well. This will help us to guide the program to give us proper meshing. And then later on, you can easily just use a auto capability of MIDAS to do the meshing. I'm not going to mesh it right now because it will take me a extremely long amount of time, and I'll just show you what needs to be done. And properties, properties, as I showed you before, is probably the most important thing. It needs to be done first. Properties needs to be defined. We have them here. We define our soil layers, the wall, the ribs, everything. So that should be it. After meshing, the next stage would be defining the boundary conditions. And boundary conditions is where it actually becomes important for dewatering phase. So the first boundary condition that we definitely need is going to be the constraints that will give us the exterior of the structure. We use the auto boundary feature of MIDAS, which automatically goes and fixes the degrees of freedom that needs to be fixed. And after that, so all these other boundary conditions that I have are correlated to the watering feature in the MIDAS. And in order to do that, we need to come and use nodal head feature that is incorporated in the MIDAS. So for example, for this specific case, my assumption was that the initial water is at ground level. So with a nodal head function, so if I want to come and edit it, I can show you what we have defined. So we have given a 0 feet total head for all these nodes. So basically, we have defined the water head to be the same as y equal to 0. And then later on, if I go and turn off the mesh and I just keep the excavations on, I'm going to show you the dewatering stage now. If I go to the boundary conditions, so under analysis, under boundary conditions, again, we have defined, so we go and tell to the program that I'd like to reduce, so this is each of these stages is 10 foot. So we go and tell the program that we want to reduce the water head for these nodes up to -20 feet. And then there are different stages. So for example, in excavation 2, same thing goes and happens here. So at each stage, we go and tell the program that you need to dewater further and further. And in one of the examples, I will go and show you how the program is going to implement that and how the results is showing. So what else? And of course, obviously, we will have our gravity, which is basically the dead weight of every element. We need to apply that. That is a must-have. I know everybody knows that. So we apply the self-weight of the system. And we don't, in this particular case, we don't use any other material change or dynamic load applied to the system. So I'll just quickly go over the different stages I have defined for this specific analysis. And so as you can see, I have two different models here. One is with dewatering, which I have dewatering stages also defined, and one just with dry material properties. I first go over this, and later we will go over the one that has dewatering also incorporated. So here I want the program to show me the active stages. So what I do is I put all the soil layers I have all different excavation layers I have, and then I also apply the boundary conditions to the system as well as the self-weight. In the next stage, I go and in the next stage, I go and I go and define the wall to the program. This wall is the exterior shell element that we use to. So, for example, in this specific case, we have a diaphragm wall that is a shell element, and we go and define it here. Later on in the next stages, we go and start excavating all the way to the bottom of excavation 1. Again, this is in this specific model, we really don't have any dewatering modeled into the system. Similarly, we just keep excavating all the way to the BOE. And obviously, if you have ribs or anything like that, you also will apply that as you excavate. Now I'd like to go over the dewatering, because that is the one that has a little bit more challenges. So you need to make sure that when you define your analysis, so if I want to define a stage analysis, you need to make sure that you go and select the proper analysis case, which is a stress, seepage, slope option, which is the third one. And then the seepage analysis case is a steady state case, so you need to make sure that you go and select the right stage there. And the boundary set that you need to apply for this stage is basically that the water level is going to be at the initial level, and then every stage you need to have one stress analysis, one steady state, one stress. So they go hand in hand to give you a coupled type of analysis that considers both water and stresses. So, for example, now I do apply my boundary set, my boundary conditions, and I also apply my gravity. And as you know, this is going to act as my initial stage. So typically, I would just tell the program if I want to clear out the results. So whatever happens afterwards will be the results of my excavation. Again, the wall excavation, the wall installation, which is just a stress analysis. And you know that the wall installation is its own process and procedure. If you want to consider the wall excavation on its own, you can have a separate model developed for wall excavation to analyze all the ground displacements that occur during wall excavation. Again, in the first stage, what I'm going to do, so here, as you can see, I have activated the boundary set excavation 1, which if you remember, we dewatered all the way to 20 feet. And this is a steady state analysis. Later on, we do similar thing. We do the excavation and we apply the steel ribs. And this will be repeated all the way to the down. So one steady state analysis that you change, or you also need to change, you need to deactivate the old boundary set and activate the new one. Again, one steady state analysis, one stress analysis. So this is the way it's done all the way to the bottom, and then later on you need to define your analysis cases, which I would just go and just give you a hint. So for example, here we have two options: the analysis without dewatering and the analysis with watering. And always make sure that you go and check the proper. So for example, if you want the load to be applied in multiple stages, make sure that you have that applied. That could save quite a bit of time. And all the other nonlinear analysis details that you want to incorporate. Without further ado, I would like to just go and go back to my slides after giving you a brief description of how the modeling works. I would like to go back to so I have covered this. I have already covered this one, covered that one. Okay, so after you do the modeling and you let it run for quite significant amount of time, the program, let's not forget that what we intended to do, we wanted to analyze a existing structure, a facade of existing structure due to excavation. So what I'm interested in, I want to know what settlements and what plane displacements I get out of my analysis. And let's say, so for example, point A, point B, point C are the exterior facade of this specific building. And I go and get the outputs out of the program. So for example, here I'm just showing the X displacements, what you expect. And here I'm showing for the same nodes, I do Y displacements. And here I do the Z displacements or settlements, if you want to call them. And here is just, if we assume X and Y as two vectors decomposed in X and Y direction, XY plane will be the combine of X and Y displacement in one graph. And let's go back to Berland and Ross method, which uses, so basically I had point A, point B, and point C. And I wanted to see how the facade of this particular structure is going to act. So I go and using MIDAS, using the magic of MIDAS, I go and see what settlements I get at these points, and incorporating that into Berland method, I will be able to know what strains I get. And what I'm interested in is obviously we had two components. One would be the bending component, and the other one was the shear component. Applying the equations coming from the research of Mr. Berland, we get the strains, the horizontal strains, the diagonal strains, and the total strain. And the total strain for this specific case under this specific soil conditions and everything, the maximum strain I was getting was 0.007%, which would fall within the negligible zone as we defined all the way back in the purpose of our analysis. No, I guess we are early. So here, yes, here we defined the critical numbers, the limiting tensile strains to where the negligible zone is, where slide is, and this is what we did for quite some time, close to 2 years, for northeast boundary tunnel, and all the structures and bridges that were impacted by different excavation activities and different underground activities we had. We analyzed them, whether they were buildings, whether they were utility lines, whether they were bridges, depending on how significant the displacements are. You will approach each problem individually, and that is one of the things that we at STE we have quite amount of experience doing that. I guess for now, let's go and see if there are any. JC, are you with me?
Yes. Yeah.
Okay, perfect. So
yeah,
if there are questions,
thanks for that presentation.
Yeah, sure. If there are questions, we can go and answer the questions, and based on that, we will proceed. If there are things that I need to go show further things in the model, I would be glad to do that. Let's go and see what feedbacks you're getting from our participants.
Right. So far, there's only Stanley from Canada, but his comment wasn't really related to the presentation. He was just asking us about some stuff. And so for the rest of the attendees, you can submit your comments and questions in the question panel of the GoToWebinar tool. So if you type anything, you can send to all of us so that we can see that. That'll be great. And so, yeah, I just want to thank Parsa again for the presentation and the very detailed guide of how to create the model in GTS-NX. I actually have one question myself personally.
Sure.
So yeah, so the structure you're analyzing, so that's the A point, B point, and C point. How far is that structure actually from the shaft?
From the excavation?
In reality, yeah.
In reality, first of all, I think it's about less than 50 feet. I can double check in the model and I'll get back to you. But it's I guess less than 50 feet, the closest point. to the extent.
Right. So that's the same distance from the settlement ABC point to the shaft in the model, right?
Yes. So basically, the closest point on the structure to the shaft has less than 50-foot distance. But as you know, these settlements are very dependent on what type of soil you have. That's extremely important, and that's the most major thing that you need to look for, what soil you have. So that's why I really believe that every single case is an individual, requires an individual investigation. These are very highly dependent to this, to the geography, to the soil types and soil layers you have, and one analysis to the other can vary quite significantly.
Right. So yeah, I saw that you modeled the soil using a Moore Coulomb model, and
Yes.
I know that shear plays a really important factor when it comes to like Moore Coulomb material failure. So like, how did you, because it's such a like a sensitive material model, how did you determine like the right material property, like different coefficients used for this model?
That is a fantastic question. So actually, so for example, in northeast boundary tunnel, typically the owner gives you the number that you are contractually obligated to use, because these numbers are extremely important. A small change in any of these means a lot, and you are responsible. And typically in the GBR and GDR, the owner gives you what number you should use and what numbers you are responsible for. And if in the real world, the real numbers are different from what was described in the GBR or GDR, then there will be a lengthy discussion of who is responsible. But thank you for that question. These numbers they mean a lot. So increasing or decreasing each of these properties by 10% could be very significant, and there is a huge responsibility behind these numbers. And typically, what you use is described in the contract. So if you use something outside of the contract, you're fully responsible for it.
Right. So you said you also used programs before. How's the Moore Coulomb or any like nonlinear material model in MIDAS? You know, how's the application different from like your experience with other software?
I'm quite familiar with FLAC, and I would tell you each of these programs. What I like about FLAC is the capability of working with it as just a simple computer programming software, which I like. So when you're happy with your FLAC model, it just becomes a regular computer code similar to what you do in C++ or MATLAB or anything else. That's what I like about FLAC. What I don't like about FLAC is that GUI is really an afterthought. They had FLAC there, and then later on they said, okay, now we need a GUI for this. What I love about FLAC is how user-friendly it is, how straightforward things are, and I would tell you that for regular use, definitely MIDAS is way more straightforward and easier to deal with than what FLAC is, at least my personal experience. And also, so in terms of visualization, I would say MIDAS is miles ahead of FLAC, at least in terms of workability, in terms of ease of use, in terms of, I would say there are two different worlds, to be honest.
Right. So I think there's questioning the audience, saying like, what if? So in this case, the house is the thing you want to kind of see the string at. So would it be any different if it's something else? For example, a bridge.
So basically, I would say it depends. So for example, typically if you have a bridge, you no longer can apply greenfield assumption. So if that bridge is built on a deep foundation, you most probably, what they expect you is to have it properly modeled in the system. So if you have a group of piles, you need to have those group of piles, because bridges typically, at least based on what I have seen, the bridge owners, they don't let you go that easy. So if for a 2-story building, I can go with a greenfield assumption, for a bridge, most probably they will not let us do that. They want the foundation properly be modeled inside the MIDAS. They want the piles, deep foundations inside the model. If you have a concrete pier, they want that in the model. If you have, so definitely you will not have the deck in the MIDAS, but they want the proper loads on that foundation. So whatever the governing load you had from your bridge design, you'll need to apply those. So bridge, I would say, generally speaking, that's not really much different from this, but there are a little bit more details if you have a bridge, especially if it's on piles. You need to be way more detailed, incorporating especially piles. They will not let it go.
Right. So has STE worked on any like particular, I guess, evaluation project for bridges in these areas?
Yes, we have. Yes, we have quite a bit for WMATA, especially WMATA and DDOT. We've especially the pile structures. We've been involved with multiple bridge analyses over there, especially under displacements due to tunnel excavation. And yes, we have quite a bit of experience over there. Yeah.
Mm-hmm. You also use GTS NX for that analysis?
No, we use FLAC. I use FLAC.
I see. Okay.
Yeah. Yes.
Cool. Yeah, I actually don't see any more questions from the audience, but I think a lot of people join just to, want to, since this is a workshop, they want to kind of just see the process, and I think it will be a good experience for them to, like, even without question, just to see your demonstration and your experience. So yeah, I'm pretty sure that's really helpful. And I really like your demonstration on, like the controlling nodes, and because I know like creating mesh has always been like a very important point.
That is one of the things that could give you hard time. Defining proper mesh is a key in any finite element type of program. Without proper meshing, just forget about it. Without proper material properties, forget about it. Garbage in, garbage out. The properties are not right, you will not get anything right out of it. The meshing is not right. Again, that will give you a hard time. In many cases, if your meshing is not right, even the program can diverge. It will just not work. So yeah, I totally agree with you. Meshing is important.
Do you have any tips for, like how do you judge what is a good mesh? What is like a problematic mesh?
Typically, there is no magic behind that. The best way of doing it is at the starting stage, you need to do a mesh sensitivity analysis to see what mesh size is good for that specific model, how big or how fine, or how coarse you can go. And you need to do multiple runs in the beginning, doing a mesh sensitivity analysis. And after you realize what mesh size is that golden ratio, then you can just stick to that, and then you keep working with that mesh size for that specific model. And in the next model, you need to do another mesh sensitivity analysis.
Right. So for the mesh that you use for this analysis, for example, did you just, so was your mesh size related to the material property, or it's just arbitrary?
No, yeah, it was more based on experience on
I see.
this specific, yeah.
Okay.
Now, I did quite fine mesh. The mesh I had was decent. Based on what I've seen, I would say the mesh was good.
Right. Yeah. So I do see some thank you from the attendants. Yeah, I think people are running out of questions, and I think it's closing time, 4 o'clock. Actually, one more really quick question, just from personal note, and also for those of you who want to review this session will be definitely online, and yeah, and there's going to be useful like tips and being put on the Bridge library as well in MIDAS page. So make sure you review these. So yeah, like a personal note question from me. So what's the difference between, you know, like just doing this excavation sample example between like the 2D model and the 3D model? Like I was just imagining, you know, cutting the section in half and just do like a 2D model of the cross section, and like have you done that kind of analysis?
That's a very good question to ask, actually. So for example, 2D versus 3D becomes problematic, especially when you have geometries like this one. So for example, so let's say for a circular section, if you do an axisymmetric analysis, 2D versus 3D will be quite comparable. But if you, so let's say you want to do a 2D analysis for, so look at the, so let me do a result, so XY. So this is the displacements for this specific excavation, both X and Y direction, right? So let's say you call this direction X, you call this Y. The 2D analysis for these two are not, you can't use one instead of the other. So you need to have a 3D analysis to see that, okay, we have quite a bit of displacements located on this side of the excavation, but on the short side, we really don't see much. If you want to do a 2D, of course, you need to go with a conservative assumption, and then you will assume all points are doing similar to this long direction. That is actually something that we typically did for Northeast Boundary Tunnel. You always need to go with a conservative assumption. So even if you are located here, you assume that this type of displacement will occur, which is not right. Did I answer your question?
Yes.
Okay, but for a circular cross section, because of the symmetry, you will have way more comparable results than a rectangular excavation. If that is if that answer suffices.
Right. Yeah. So yeah, I was just curious because it's a circular excavation, and
Yes.
you know, you mentioned symmetry. So
Yeah.
why didn't you just use a 2D analysis instead of a 3D one?
So the purpose of this analysis, the purpose of this session was going through a 3D, but we definitely can do a 2D and we can compare it as well. So yeah, that's doable. You do an axisymmetric analysis, and that should that should also work quite well.
Okay. Sounds good.
Very
All
good.
right.
Next question.
Yeah.
Very good questions. Very. Your questions were showing that you have a great insight to the matter, which always excites me. And if there is any other thing, I would love to answer. Otherwise, I guess we should be able to just end the session.
Yeah. Thank you, Parsa. I think the audience, a lot of them actually find it very helpful, and they stayed until the very end. Yeah, I just really appreciate everyone who showed up, and I appreciate Parsa your time, and Amir your time for your introduction to STE. Yeah, this is a really great presentation, and I just want to say, so this is the last workshop session that we're planning to do this year. And yeah, really appreciate your time, and it really proves us that like why we're doing this, and trying to kind of prove our effort to build a better user community and having a better conversation among users. But yeah, we haven't really finalized like the list of topics for next year's workshop and Q&A and webinars, but definitely we can check out our Metasoft bridge page to like kind of see what's going on next year. But other than that, I'm just gonna close here. Thank you again, Parsa. Do you have any closing notes?
No, not really. I wish everybody Happy New Year and Merry Christmas to everybody. And I guess that's it.
All right. Thank you so much.
Have a great day and bye.
Yeah, you too. Bye-bye.